let me now introduce our first speaker. As for our first speaker, Provide Zeng was trained as an architect and a researcher. Her research concerns the emergence of digital tools and their impacts on architecture and urbanism. Her current research discusses how large scale computation prompts a preemptive urbanism, where blockchain and machine learning helps to facilitate and computation data market that transforms into digital twins, into digital assets, and guides our design strategies. In her design work, she experiments with all multimedia narrative as a control and communication technology, which expands the audiovisual spectrum of architectural representation. Let us have architect provides. No.
Hi, everyone. Good morning, good afternoon, and good evening from where you're attending this webinar from. My name is, I see myself. Okay. My name is Provise. I'm very excited when I received the invite from UAP, especially when I saw that the theme of your event, the quantum leap in architecture, it is an excellent opportunity to begin an interdisciplinary discussion about what had happened and what is happening in the natural science fields, and to bring that knowledge into social science, and to discuss what it might mean for architects as designers to encounter a quantum leap. So should I share my slides? Hope you will be able to see it. Okay, cool. Share screen. Do you all see it? Awesome. Okay. So today, I have decided that instead of giving you a talk, I would like to tell you a story and map a timeline of events backwards. We will begin with what it is that we're leaping over today and scale down this planetary urgency to the atomic level, more specifically the carbon atomic level, and to discuss how we may begin to quantify it and design towards it. Then we will go back to the 20th century, where humans' exploration of quantum events first happened. Finally, I will illustrate how this might go in the future with two projects that my team had been working on. Before I start, I'd like to tell you a little bit about myself. So my entire life is on Instagram and YouTube. As it is written, I'm a pseudo architect, whatever that means. I am currently teaching at the UCL. I do interdisciplinary research. But the more important question is, what is the role of media in shaping our social economic trends? And how can it extend beyond entertainment? While my parents, they're from the boomer generation, I can imagine that most of you here are probably from the Sumer generation. So what's the difference between now and then? And what are we leaping over? I can see we're still basically wearing the same t-shirt. But today, with no surprise, most of our lives are on social media, which became an inseparable component that guides our everyday lives. And the media also guides our modes of production and consumption. But the urgent question is, how can the design of media and our digital tools help us in collectively steering towards a desirable future instead of a dystopian one? Well, I believe that the future is not urgent because it is already here, but our action is urgent. So how can we decarbonize through design? That's the thing that we're leaping over. The design discipline is a practice of abductive reasoning. Here, I shall quote Professor Keith Dorst. In contrast to natural sciences, which largely operates on deduction and induction, design abduction is used when we want to create something of value, and that leads into the design territory, the problem-solving territory. You see, in most fields of reasoning, you would at least have some sort of conception about the what or the how. So you would be able to describe the problem structure and be able to capture them computationally and precisely through natural and mathematical languages. But in design abduction, we only know the outcome that we would like to achieve. I would argue that during a large period of our lives as designers, we don't even know what that is. So the best designers are those who can tolerate the most uncertainty. then the question becomes, what is it that we're aiming for? What value that we wish to generate? And what would be the thing that makes it all work? Oops, I have a Facebook notification. So in the space where climate change mitigation and building design overlap, there's green architecture, which is an approach to building that minimizes the harmful effects of constructions on our environment. Nonetheless, the spectrum of color should really be expanded to accommodate more than just one class of building that passively assures ecological health, but a full category of functionality that actively recovers our geoconditions. For instance, there should be a spectrum of green architecture that is not only designed for energy efficiency, but actively functions to facilitate, let's say, regenerative agriculture. There should be red architecture, which functions for the support of forest fire resistance. Blue architecture for ocean ion fertilization. Yellow architecture for carbon capture and storage, CCS. And brown architecture for soil carbon sequestration, and so on and so forth. These are but some examples that I'm putting on the table for now to start our conversation, but the spectrum should really be expanded to accommodate many, many more colors. Along these lines, there are three main questions that I would like to investigate. First, how much human, architectural, infrastructural, and economic capital will such an active decarbonization system demand? Let's take the yellow architecture as an example, which is carbon capture and storage. According to Jean Holybuck, under our 2-degree carbon budget, we will have to capture and remove 10 gigatons of CO2 in our atmosphere by the end of the century, which is 2100. To capture 1 gigaton will demand about 1,000 facilities. To capture 10 gigaton, we will need about 10,000 facilities starting from this moment, but presently we have about 22 of them, so we are far behind schedule. This means that we will need not only architecture, but infrastructure on the order of the existing fossil fuel industry. While it took more than a century for our oil industry to get to where we are today, but we don't have another century to lose. We will need decarbonization strategies that can generate profit as much as fossil fuel, if not more. In order to realize this amount of work, our architectural pedagogy is at the forefront. So the second question becomes, how many do we have to educate in order to decarbonize? Well, that's an economy of architectural education in itself. We will need a large capacity of architects who are equipped with such forms of interdisciplinary knowledge. On the other hand, the design of decarbonization system is an interdisciplinary problem. So we would need means to search for tools that falls between the established fields of expertise, promote cross-exchange, cross-communication, and cross-stacking. Last but not least, different countries have different latent carbon capacities due to their differing available natural and artificial resources. For instance, if we look at Sweden, Sweden has about 4.5 gigatons of CO2 storage space, whereas Norway, which is just next door, has about 21 gigaton capacity. Potentially, the two countries can negotiate on carbon trade and have some of Sweden's shipped to Norway and have it stored under the ocean. If we look halfway across the Earth, China has about 65 to 1,500 gigaton storage capacity. As you can see, the gap for approximation is relatively high. The reason behind is that there are always unpredictable fluctuations in geological and demographic factors. As you can imagine, the larger the country, the larger the uncertainty. So this is where speculative design comes in. As a way of understanding it, we live in a complex system where simple components interact to give emergence to complex phenomena. Climate change is a complex natural phenomena to which humans and our social economic organization is part of it, meaning that we are within the complex system itself. So that's the paradox. How do you describe and capture a complex system while being inside a system, not being able to have an overview? For instance, if Europe put up a law on carbon regulation, it might give emergence to shadow economies in Indonesia, where people are dying of toxic substance from this rubbish Mount Everest. meaning that everything that we do has a causation consequences that we might not always be able to observe. But the bright side to the story is that the undesirable presents have taught us how to speculate and act against undesirable futures. So, for instance, if we are to propose a step one in our design, we might then have to speculate on all possible futures that can emerge out of the best we can, and then reconfigure our situation-based solutions iteratively from all these speculated futures. It's like a decision tree. If we go back to the China example, let's suppose China only has 65 gigaton capacity. How should we design for step 2 and 3? And if we're basing on the 1500 gigaton scenario, how should we change our strategy? So it is an iterative feedback between the present and the future across disciplinary and geographical borders. So if we look deeper into what speculation actually means, speculation originates from the discipline of finance. A finance speculator has to consider what is the present action one should take so to minimize the choices of one's opponent in order to maximize one's total payoff. So it's basically game theory. Presently, our opponent is climate crisis at the planetary scale. It's so complex that we can't have a decision tree which maps all possible futures where the branching factor would simply be too large. So how can we even begin to design? One way is through knowledge networking, exactly what we're doing right now. But more than that, we have to be able to index and standardize our protocols. So all the numbers I pulled from different research about carbon capture and storage, they are projected based on different estimated scenarios, right? So all these will have to be calculated and indexed according to variables such as the mass of population in a country, how much energy a country is exporting, and the support for global consumption, etc. So it's not as easy as saying that one country seems to be over budget on numbers and we just focus on regulating her, but more like how to have a planetary scale collaborative index on such numbers according to what variables, what scenarios, what designs. Most importantly, we need media to synchronize this knowledge. So these are some very important questions to ask for any designers who wish to participate and design for the changes for the LIP, for evolutions in our social economies. So now we have partially discussed the values that we want to generate. But what will be the thing that make it all work, that make it all evolute? That's the question. And to discuss evolution, we have to turn back our clock a little bit and go through some history. Now we have come to the fun part of Quantum Leap. So this is a book that studies evolution very well. It is one of the first books that also discusses quantum leap. So it's interdisciplinary. It brings together evolution and quantum mechanics. So how can it be used to understand social biological evolutions? We are now in the 1944 when the first edition of this book was published. At this point in time, Einstein had already proved the existence of atoms at the age of 25 using Brownian motion. Yes, most people remember Einstein's contribution at the macro scale, general relativity, but actually his day-put work is at a much smaller scale of the universe, the atomic scale. And so in 1944, this guy Schrodinger was thinking, while physicists were able to explain a lot of things that happen at the very, very large scale, the astronomy scale, but why are they not able to understand things that happen at the electromagnetic scale, the social biology, and at the very, very small scale, the quantum mechanics? And most importantly, we're not able to understand across scales. So he suggested we can use a naive physicist approach where we observe a system and identify a problem that is interesting to be solved and hypothesize on the reasons that leads to some complex phenomena. But we may not always understand everything through their causal relationship. Instead, we may understand them by their correlation. So he stated that physical laws rest on atomic statistics and are therefore only approximations, and their precision is based on the large numbers of atoms intervening. Thus, our physical laws at the macro scale are actually just an approximation of what is happening at the micro scale. This is a formulation to the study of complex systems by their correlation. and established one of the most fundamental laws in quantum physics, which is quantum probability. From this, he moved on to discuss social biology and proposed that the inheritance of our genes from our parents is too perfect to be governed by the rules of classical mechanics, so quantum mechanics must be playing a part in it. He is basically saying that evolution is based on mutation, which is based on quantum phenomena that are probabilistic. For instance, our recent science advancement had hypothesized that quantum jumps might be a mechanism that can be used to explain adaptive mutations, which can be used to explain jump-like evolutions, where the best social biological future can be survival. The worst can be cancers. But in order for us to understand what is the connection between quantum mechanics and social sciences, we have to first understand what is a quantum jump or a quantum leap. A quantum leap is the abrupt transition of a quantum system from one quantum state to another, from one energy level to another. So when the system absorbs some energy, there is a transition to a higher energy level, which we call excitation. When the system loses energy, there is a transition to a lower energy level. So some of you who have studied physics in high school, you probably remember this. So the theory of quantum evolution help us to imagine the processes of our social biological changes. For instance, in the case of genetics, we can imagine that the configuration of DNA in a cell is held in many multiple possible quantum states. So that's quantum probability. And mutation occur as a result of a collapse of the multiple possibilities into the best configuration of the cell. So it's basically saying that our DNA selects one from a multitude of possible outcomes, speculation. And when you map human evolution, not only does it look like a decision tree, it is not a smooth curve where we have jump-like mutations that can be observed. So Schrödinger described this as the discontinuity of mutations, and he moved on to stating a remarkable general conclusion that the collapse of multiple possibilities produces order. So what does it mean by order? We often talk about order in architecture and in design, but it's very different to what order means in natural sciences. According to the second law of thermodynamics, it is stated that the level of disorder of any isolated system always increase. So if we imagine a system of gas, the gas will naturally dissipate and sparse out if we do not put any energy to hold the gas together. And the measure of this disorder is called entropy. Basically, it is the measure of how much unavailable energy is there to do useful work. So if we look at social biological systems like our body, it doesn't just disintegrate, right? So Schrödinger concluded that living matter evades the decay to equilibrium. Thus, living beings always minimize entropy. We are fitting on negative entropy, and organization is maintained by extracting order from the environment. This has very specific design implication, meaning that we can maintain negative entropy by creating order. But now we're back to the question, what is exactly order? So all these quantum theories are very exciting. Let's take a moment to take it in, and then we will begin talking about what it actually means to designers. I'll take some water. Okay, are you ready? Let's go. We are obviously not the first one to imagine a quantum future in design. So this guy is Gordon Pask. I don't know if you guys know him. He's a very famous cybernetician. He has two very incremental theory that he theorized in the conversion of quantum mechanics and architecture. The first one is conversation theory, which is basically a dialectic framework that offers a scientific theory to explain how interaction between humans can lead to the construct of knowledge or knowing. The second theory is the interaction of actors theory. This is something that is very deeply embedded in our everyday life that we might not even notice. For instance, every digital platform is based on the interaction of actors. So it came from this 20th century exploration. between quantum mechanics and social science. It's basically a generalized account of the kinetic process that support conversations, bounded by the beginnings and the ends in all media. So very obviously, it has a philosophical base in Sigmund Freud's psychodynamics and cybernetics. So what's the significance of this in architecture? Like, what can we get out of by comparing quantum mechanics and social sciences? We might understand this better with a very obvious example that's more adjacent to us. So this is from Patrick Schumacher from the Zaha Hadid Lab, which I think will tie very nicely to our next talk by Mariana. So the idea behind this is that if we are able to capture any processes from natural to social biological processes with a partial differential equation, which we can probably get out of from classical mechanics or quantum mechanics, then we are able to analyze the social biological processes from conversation to interaction using finite element analysis, which is a technique that Zaha Hadid Code use a lot nowadays, especially with Schumacher's understanding of agent-based parametric semiology, which explores how the built environment can be designed as a system of significance that communicates the complex spatial structure and a rich offering of designated spaces with diverse programmatic contexts to a multitude of interrelated user groups. Basically, it's saying that if we're able to identify between different scale of social formation from intimate, personal, social to public, we will be able to capture them computationally and generate spaces according to these variables. So you can see that Schumacher's approach shares a lot in common with Gordon Pask's approach. Well, that's because one of the very first books that Schumacher publicated was Autopoiesis of Architecture. Well, that's a cybernetic theory from complex system, which aims at capturing social biological processes. And when we are able to theorize them, we'll be able to use alternative process theories that conform with the same principle to test out different hypotheses. So let's remind ourselves of Gordon Pask's conversation theory. It's basically based on quantum entanglement. So quantum entanglement is a physical phenomena that occurs when a pair or a group of particles is generated, interacted, or share spatial proximity in a way such that the quantum state of each particle cannot be described independently. So I've put that in parallel with a sketch that Pask drafted in the 20th century. Basically, you can see how he tries to map a conversation using the quantum dynamics. And on the right-hand side, you can actually see a formulation of the Fun Palace by Cedric Price. And above that, that's actually one of the first sketch by Gordon Pask, who sketched out a mechanical approach to architecture. As we all know that the Fun Palace focused on automation to enable diverse interaction within a spatial environment, right? But in order to enable that, we would have to understand the conversation dynamics. And then we can see nowadays that the Centre Pompidou in Paris embodies all the spirit of this. So there's a story in history that we can trace in order to understand. Well, for instance, what do we have to automate in architecture? Why are we automating that? What are the values that we want to achieve? So from this point, I really conclude a few thoughts. The first is probability, meaning that the boundary to any system has a statistical meaning. If we remember quantum mechanics, we cannot understand them by their causation, but we can understand them by their correlation. So that's a statistical meaning. And we should always design while paying attention to the statistical boundary, meaning that we have to accept uncertainty. That's very uncomfortable. If we go back to our carbon capture and storage example, how do we even begin to design for China that has 65 to 1,500 gigatons of carbon capacity? So that's exactly a statistical boundary with no absolute or definite answer to interacting carbon systems. And the question is, how do we even begin to imagine all possible scenarios? If you remember this brilliant guy I mentioned at the beginning, Keith Dorst, he did a psychological research into successful design students. Well, that's hard to say, but basically he looked at the psychological measures and then the correlation with success. He found that tolerance for uncertainty came up tops. So meaning if we're able to tolerate uncertainty, we are more likely to be successful design students. Anyways, how do we even begin to tolerate uncertainty? And how do we identify a statistical boundary to a system and begin to work with it? One way to think about this is that to design is to create order. By order, it is not the Cartesian grid, the grid with the XY set that we are very used to in the computational space. But order means to minimize uncertainty. Well, that's from the second law of thermodynamics, entropy. So it is to first know how much we don't know, to first know how much unavailable energy there is, and to first design a measure to this uncertainty, which is basically entropy. So Schrödinger puts it very poetically. Much more important for us here is the bearing on the statistical concept of order and disorder, meaning that there is a statistical meaning of entropy. And this is what it looks like in action. So I don't know if any of you study physics. I briefly studied chemistry in high school. Entropy equals K log D. Well, K is a constant, so we can just pretend it's transparent for now. D is a quantitative measure of the disorder of a system, and the logarithm of D increases with D. So what this mean basically is that the left side to the formula is the macroscopic observation of a system. And the right side to the formula is the microscopic view based on the rigorous treatment of a large ensembles of microstates. So this one formula, it's so amazing. It's so beautiful because in 5 symbols, it already provide a descriptive linkage between the macro and the micro scale. And it means for us to comprehend across the scales. It's so simple and beautiful. So understanding the entropy of a system enable us to capture across scales and to derive how much energy we have to input into a system. Well, design is the sign of how much energy we input into a system. In order to achieve a desirable state, identify the mean of input is the act of design. So this leads us back to the quantum leap. If you remember, when a system absorbs energy, there's a transition to a higher energy level, meaning that design is an abrupt transition. It's jump-like, especially for decarbonization design. If you still remember, we don't have another century to lose. If we suppose that excessive greenhouse gas in our atmosphere equals disorder, because the gas we release dissipate into equilibrium, right? Then the measure of the disorder of this release of gas is entropy. Then the capturing of it is the negative entropy. Meaning energy input is needed for us to transit to a higher level of order to capture everything that we have released into the atmosphere. But how much energy is needed? In what format is that energy? Well, that kind of excitation is the leap, is the design itself. And in this way, we can beautifully tie every establishment we have made in physics and mathematics to architecture. And we're able to input them in a computation system and be able to simulate that and to make decisions based on the speculations. So design is based on abduction, very briefly to summarize, which is uncertain. And based on defining the statistical boundary of a system, the input of the energy is the design. Okay, now we take a sip of tea and inhale these thoughts for a brief moment. And then we will proceed to the last part of this talk, where I will discuss 2 projects that I've been working on and my teammates we have been working on to illustrate my arguments in a clearer manner. Okay, water. Ready? So the first one is a project by my team. We are the Rational Energy Architects. We call it REAR. That's actually also a joke. It's always so good to have some humor. We aim at rationalizing energy with irrational numbers. So that's our branding, it's our tagline, rationalize energy use with irrational numbers. Okay, especially for social media. So we introduced the component of information into the whole framework. Our project is one that used an information theory approach to biodesign. While biodesign is an interdisciplinary study between fields of biology and design, one of the fundamental problems concerning both fields is the understanding of the relationship between an individual and its environment. For architecture, individuality is the quantitative measure to which designers evaluate the performance of a design relative to the inhabitants in a built environment. For biology, there are common assumptions on individuality with diverging fields on its identification, the exploration to which, using information theory, advanced the discipline from a biology of things to a biology of processes. So this enables us to apply mathematics as a language for describing complex systems and their emergence from organisms to organizations, and potentially be able to capture them computationally. Our work compares two emerging fields in the biology of processes, the Gestalt approach and the free energy principle. And we inferred from this comparison ways to streamline, engage energy, supply, and demands. Both fields study how information is feedbacked between the interior and exterior of a system in an iterative manner. So the Gestalt approach argues that individuals are aggregates that propagate information from their past to their futures, where we may begin to describe the performance and qualities of an individual by their variation in the degree of environmental dependence and inherited information. In other words, a measure of entropy. Whereas free energy principle argues that the consideration of how an individual maintains the boundary that delimits itself is the key to understanding self-organizations. Where individuals have access to information on their individuation. Thus, biological systems tend to minimize entropy, which is the average level of disorder or surprises in the information on their environment. They do so through active inference, so active thinking, prediction, and action. Active inference is what interests us, which is how an individual uses an internal generative model to predict incoming sensory data. From the two fields, we extrapolated three main points of how an individual, be it a building component or a building system, can perform active inference to minimize entropy, where information is used to learn and represent energy and spatial circulations. First is negentropic design, which thinks about the conservation of energy through the creation of order, where order is not the Cartesian grid, right, but the boundary to the system, and how energy is transformed and transferred from one to another, and is manifested and quantifiable in the transmission of information. So through defining the statistical boundaries of interacting systems over time, for instance, using model, the information ensures an individual's first right to act in order to minimize entropy. So that's the financial speculation that I mentioned before, first right to act, which is leading to the second point, preemptive design. All of these are so that we'll be able to hypothesize optimals in information communication using topologies, which can be translated or compared as a datum to physical constructs from architecture to infrastructure. Well, then you may ask, how can these infobiological theories be operable in architectural design? So we tend to illustrate this with two design experiments that we have been working on. The first one is form finding for carbon nanotube-backed solar cells. So carbon nanotubes are carbon atoms being lined up in a tube structure with nanoscale diameters. They have band gaps that highly matches our solar spectrum. Thus, Carbon nanotube possess immense potential in photoabsorption, and it can be fabricated as semi-transparent and flexible conductive films, which is ideal to be layered over both linear or curved facades as light harvesting material to achieve self-sufficiency and self-organizing energy systems. As part assignments in space finding for optimal patterning and coverage while leveraging aesthetic concerns and indoor microclimate like light diffusion and sun shading is essential. So our challenge is to assist energy efficiency by optimizing physical pathways to which electrons circulate while considering the possibilities of global geometries that are self-standing. So the panels can be made available not only to new buildings, but adaptive to existing ones at low structural costs. Thus, form finding can be a means to minimize entropy, minimize energy dissipation during transfer. For instance, when electrons circulate in a physical channel, it induces heat loss. So how can form finding designs help us in tackling that? We can begin by thinking about how solar cells can self-organize in a physical network, and we figure that we will have to achieve three things in its formal organization. First is to minimize the physical pathway to which energy circulate. Second is to achieve a more equal energy distribution to enhance energy flow. Third is to produce variations to be adaptive to indeterministic environments. So based on this, a solar swarm structure is proposed. This structure was designed based on the Hadley cell, which is one of the atmospheric circulation on Earth. It transports energy polewards. So it reduces the resulting equator to pole temperature gradient for more equal distribution in energy transport. A vector approximation is performed to resolve issues in fabrication. The possibilities of backscattering light is considered by layering carbon nanotube on one side and reflective materials on another, to which the global geometry can absorb tension created by heat expansion of the two different materials. As such, efficiency is enhanced by the arrangements and the orientations of solar cells, the routes by which electricity circulates, and a more equal energy distribution from patterning and reflection. So my collaborator Baha will discuss in detail how this form was achieved. If you cannot hear him, can you please let me know?
I will be talking about the value of boundaries as integrative topological structures. The built environment is defined by a hierarchy of sub-environments as objects, with rigid projection on socioeconomic value and stakeholders' characteristics. The boundaries of these objects increase in complexity and decrease in efficiency as well as in value over time, with the risk for the built environment to become an eclectic frozen mess, where in contrast, the socioeconomic context is far more dynamic. To jumpstart a shift in inhabited structures, a two-part investigation is required. First is the shift in object definition, redefining the boundaries as the new objects, for they do not only inherit the differences between the bound environments, but also the relationship between them, therefore inheriting the DNA of their multiple typologies. Second is the value-defining process of those boundaries, to place a price tag on their flexibility and integration over time through the investigation of the iterative three-dimensional information as surfacing model and the geometric understanding of their energy tessellation in the mathematical field of dynamical systems. Strange attractors are the spatial collective iterations of multiple initial conditions of a chaotic system. The fact of being chaotic suggests an indeterministic quality, although that is true locally, yet it's stable globally, with a typology that could be rationalized. The solar swarm is an attempt on rationalizing the global geometry of a chaotic system through ensuring the developability of the surfaces. The surfaces are made of an orthogonal unified subdivision due to the solar panel tessellation technology, hence the straight bands principle. With the help of carbon nanotubes technology, it is possible to actively bend the bands into the global geometry needed. In turn, The swarm is encapsulating the potential projections of solar conditions that could morph and reintegrate in multiple dynamic environments.
Thank you, Baha. Okay, I'm not sure if you hear me. Always assume scenario. Thank you, Baha. In other words, the solar swarm is adaptive to a multitude of possibilities of solar conditions. When coupled with information systems like media platform, for instance, personalization system or collaborative filtering, it minimizes information entropy and can perform active inference to distribute energy according to climatic conditions and users' demands, and has the potential to assist a smart energy system that is not reactive to climatic conditions but preemptive, meaning to act before the climate conditions are realized. The immediate advantage is a reduction in energy absorption by the power grid, which is usually obtained from carbon fossil, thus becomes environmentally friendly. So our subsequent experiment brings the negentropic and preemptive qualities of such information system from energy to spatial organization to achieve a personalized building system and emphasis on network designs. My collaborator David will discuss in details.
In applying our research on the building level of architecture, we sought to investigate information feedback strategies to solve space shaping problems. Particularly, we looked into predicting and preempting supply and demand to optimize logistic operations. This is a response to the e-commerce spatial requirements, a thriving economic sector that can be hindered by traditional warehouses because it needs responsive measures to manage the scattered and rapid exchanges. In this context, prediction algorithm could assist in the negotiation between different actors, network of users and IoT devices, minimizing information entropy and addressing the data overload problem. Our strategy was based on Sudoku, a combinatorial game based on a 9x9 grid that can be populated by 9 distinct items. The same grid was used to discretize and encode multimodal logistic units into an architectural system, and each was computationally associated with a number from 1 to 9. These were vertical circulation, large item storage, medium item storage, small item storage, live stream space, office and showroom space, fulfillment and distribution, packaging and backend, and lastly, standard multi-use units. The computational game playing strategy can then be used to solve the organization of space by finding optimal solutions for games that are created and modified through informational feedback. Thereby, the system is able to consider time and pricing factors to define different organizational solutions for different games and states. This has potential to go beyond e-commerce and can be applied to a wide spectrum of spatial configuration problems, such as office spaces, especially during times of pandemics when individual work units are constrained by distancing parameters, and users can rent units according to changes in schedule by week.
Thank you, David. So the second project is one that expands on such integration between media platforms, information system, and urban design. Okay. So it's called Current. Project Current is a speculative urbanism project that discusses the future of broadcasting cinema and its impact on our cities. But for the purposes of this webinar, we will discuss specifically its use as a platform for Urban Archive, which minimizes information entropy in our complex urban environment by amalgamating data. And we may begin to gain insight into event landscapes that are normally beyond our perception. For instance, changes in Nordic animal behaviors, the handling of trash around the world, etc. So one of the challenges for urban archiving is an abundance of data with no simple and economic way to structure and extract useful information. For instance, live stream data from media platforms often consist of information about our built environment and its events, but such an infinite scroll of image and video data running on 30 frames per second presents immense challenges for predictive analysis. Along these lines, emerging tools such as volumetric navigation, AI image processing, and algorithmic personalization may assist us in collective information operations, such as indexing, analyzing, filtering, ranking, and synthesizing. Current focus on democratizing reconstruction techniques to facilitate a collective contribution to urban archives, instead of using high-end technologies and softwares that are mostly available to institutions and corporates. Current tested a range of lower-end sensors like mobile phones, Kinect, motion sensing, drones, open source neural networks, photogrammetry frameworks, and so on, that are all readily available to any architects or individuals. The aim is to formulate a platform that allows individuals to collectively gather and process data in real time. So this is the production pipeline that we are proposing. This pipeline enables individual users to simultaneously produce, broadcast, and acquire information through livestream. Livestream includes image and metadata like GPS and timestamps and so on, which can be extracted for environment reconstruction. With machine learning and AI, you can have estimation on what is behind a foregrounded object, so that is perfect to be paired with photogrammetry frameworks that calculates based on vantage points, and the output volumetric data can then be archived and plugged into personalization algorithms, which will label, rank, deliver recommended contents to AI image processing by collaborative filtering. For instance, we experimented with autoencoder, which is an AI image processing. It can help to fill in missing information on texture maps based on archive data, and object detection can help to estimate scene description. Finally, the output will be sent to volumetric navigation engines like VR devices and accessed by a network of users. So this basically helps to reconstruct 3D environment based on multiple vantage points from sequences of 2D images. This type of reconstruction can alter the way we navigate not just physical spaces, but mediated one as well. So my collaborators are from various professional backgrounds: computer scientists, engineer, VFX specialists like computer graphics, and artists. They each bring a different perspective to the project, so which may help to extend our disciplinary understanding beyond architecture. They will talk about their specific disciplinary views. Okay. Let me know if you can't hear them.
Current fills in the spatial and temporal gaps of information with human imagination and hopes to empower each user's own capabilities to guide these algorithmic reconstructions in ways that incorporate more diverse values and, more importantly, grow our human ability to imagine new places and potentials.
New types of seeing and navigation changes the approach for truth authentication. The shift from 2D to 3D space changes the way we think, the way we perceive. One of the best examples to understand this difference is to try to watch conventional movie in VR. First, what you notice is this disruption between the shots, montage cuts. When you're in a 3D space, it will look like a whole world around you just changed in millisecond. So the virtual environment demands a new level of continuity, let's say undisruptive media. That's why our film was made as just one shot. And we see this as a trend not only in filmmaking, but on a more abstract level in interfaces, in native advertisement, in infinite scroll feeds, and even on a more ground fundamental level, shift from CPU to GPU calculations, let's say integer to float, and from convenient algorithmic processing to neural nets.
Just imagine you can marry cinematic approaches with intertwined intercity canvas. We can make different events to be happening in different parts of the city simultaneously, or help them and adjust the plot according to what they usually prefer to watch. This can be done with scene understanding and recommendation algorithms. Another way to personalize the movie is to use generative adversarial networks to replace main characters to the viewer's faces with deepfake algorithms, or generate absolutely new actors randomly or based on viewers' preferences. Also, with the use of 3D semantic segmentation, we can reveal all actors and details of the scene, and then watch this scene with the eyes of any character we want, human or non-human.
Thank you. So we have a demo. It's a 12-minute volumetric cinema that illustrate not just what the system can output, but how such system may look and feel like for the future of our studies. It captures some of the live stream data that we've collected that reflects the urgency of decarbonization and other social economic phenomena, and we volumetric reconstructed this future. For anyone who is interested in looking at the film, please feel free to visit our website, www.current.cam. We have also developed a 3D gallery, which translates our liquid cinema into liquid gallery. It will be great to have you guys there. Very soon, we're going to have different virtual events, including virtual choir, virtual roundtable, and virtual fashion shows. So we are at the end of my talk. Unfortunately, I don't have enough time to put together a conclusion, but I think it will be best to leave a bit more time for a discussion where we may try to unwrap some of the confusions through conversation. Quantum theory. So before I end it, here is my contact again. For those of you who would like to reach out for discussion, you can DM me on Instagram at provids.ism. My name is Provides. So all of the projects that I've shown are ongoing ones. You can also subscribe to our team's social media. Find the links on my profile to follow our updates and help us spread the knowledge. Thank you so much for your attention.
Wow, thank you so much for that, Architect Provides. Now, before we introduce the next speaker, is it okay if we have a few questions for you to answer?
Yes, of course.
Okay. So, my first question would be from me myself. A personal question would be, how do you stay smart and pretty at the same time? How do you do that?
Okay, I have the perfect answer. You know, Zoom has a beauty filter. So that's a media design, right? If you go into video setting, you can touch up my appearance. And actually, the beauty filter is built on Fourier transform, which is something that came from physical mechanics. It's like how our brain transfer wave signals from the frequency domain to the time domain and then analyze that. So for instance, I would be able to look at a 3D space and I will be able to analyze this image signals and be able to locate a person in a specific volumetric space. And they use this kind of logic to make the beauty filter that we're using right now.
Well, I didn't
hope that was
expect that answer from you, but I thought you were just gonna laugh it off and just move on. But thank you so much for answering that. And
No, I did
learning
laugh.
again.
That was a cute question.
And I learned a lot again from you just based on that question. Thank you so much for answering it again with a very, very in a very smart way. Thank you so much. Well, here's a question that is well, kidding aside, as a researcher, what are the challenges that you have encountered, especially researching in this field you have chosen?
Challenges. Okay, one of the challenge is that interdisciplinary research or creatives, it's very hard to get funding. So both of the projects we are doing right now is totally a nonprofit in the sense that it's hard to get funding. The first project was easier because you can see the more immediate outcome of what it can bring to our built environment, right? But for the second project where we're talking about collectives, we're talking about decentralization and such kind of logic, it's anti-institutional. So I talk about money simply because it shows what the society is demanding as a market. If you cannot get it, it means that you are not filling in a specific space where certain people are interested in investing resources into the project. So I think the most challenge in design is to think about what the society actually needs. And I think that's most often can be quantified and qualified through how much resources you're able to get when you have tried a lot and still not able to get anything. It's a time to rethink what was wrong. Yeah.
Well, I get that. But since you already mentioned that it is hard to get funding, right?
Yeah.
So what can you advise to people that also wants to be a researcher like you in this field that we are in? That with the challenges that you have as of the moment, that is funding, that which is really really hard for me as well, because some people can't even study architecture because of financial, right? But you, as if the moment, you are really going beyond your power, and even without the funding, what advice
Um,
would you give to them?
I guess my grandmother always tell me, do not mind when you have to do a lot of free work, because you're gaining beyond the monetary value to, for instance, network effect. And I feel very honored to be invited today. And I think that's it's one of the reasons. If we actually look at Einstein, when he was 25 years old and published the 3 very incremental paper that made him super world famous, he was working in a post office as a civil servant. So he was actually doing a lot of free work. But at the same time, he managed to have an institution support for getting his PhD and stuff like that. So I think it's a choice of how it's always a struggle of how you actually balance your side project, which is going to give you the network momentum, and your
It's
job,
always a
whatever job
matter
you
of will,
have.
right?
Yes,
Well,
yes,
since
exactly.
we are already on that topic, that it's always about the will, can you tell us more on what kept you going?
Like, I think it's really all this interesting stuff. Oh, Wikipedia. Wikipedia kept me going. It's like every time I keep scrolling, it tells me something new, and it keeps me up at night. It also wakes me up in the morning. It's like, oh my God, I want to know more. So every time when I go through history of sciences, go through history of everything, I have this little cartoon playing in my head where I imagine the gossips. You know, for instance, if you have Einstein and Gordon Pask on the same table, what would they be talking about? And then from that, you trick yourself into being more curious about what actually happened. And I think curiosity, it's one of the biggest motivator for me.
Well, besides being pretty and smart, how do you how do you balance your personal life with all your readings and researches?
Oh, I don't have a personal life. You see me on you see me on Zoom 24/7. I'm serious. Okay, so I think this pandemic has created a lot of challenges, but at the same time, it is refueling the existing challenge that we have. I don't think it's it's definitely creating a lot more difficulties, but all the questions and problems that we have are existing in our society, including bad healthcare system. And also it by refueling this existing challenge, it also give opportunity. For instance, right now I'm on Zoom 24/7. Like literally, I'm able to attend conferences in Philippines, having a meeting in Europe in the morning, and stuff like that. So yeah, I think it's not a matter of balancing personal life. It's a matter of if you can find the thing that keeps you curious, and it will be part of your life. So every day I'm on Zoom. I'm with my grandmother. I don't see my friends a lot because of the pandemic. But I don't think they're separate. I don't think I have to balance them because they are just literally, you don't even have a time zone difference right now. So yeah.
Okay, why? Another question would be, since, well, we already had a lot of answers a while ago while you were discussing, and I was just in awe listening to you. But let me just ask you this: when you were a student, as right now you're already an architect, but as a student,
when I was a student, I literally graduated last in class. Yeah, both in my bachelor and my master, I was a very, very bad student actually. Sorry, what's the question?
Oh,
Sorry, for a moment it pulled me back in time and I was thinking about myself as a student and I forgot. Yeah, there were a lot of all-nighter, but then I find the problem was that I was pulling all-nighter without understanding what I'm actually doing. Call contestation or torture. It's more this mental torture about, you see everybody working and you feel that you're compelled to work without actually understanding your responsibility. So that's why I put together this presentation starting with the values that we want to generate, because I think once we understand our role as a designer, then we would able to understand why we're doing all this, why we are, pulling all-nighters and struggling and stuff like that. And it takes a very, very honest personality to be able to really see your own strengths and weaknesses and know your role, let's say within a team dynamic when you're doing a team project, is to be honest with yourself.
well, since you already answered that, yes, you did experience pulling all-nighters, and because a while ago back there when you were talking and giving us this lecture, I was actually thinking, oh, did she ever experience having a hard time? I was already on that point, but then you proved to us that yes, I did as well. But as of the moment, since I am also just a mere student, just starting off with college, what would you advise your freshman self about this field that you have chosen? What would you tell her? What would you tell the young?
I probably wouldn't do anything. Yeah, just go for it. Yay.
You'd make it in time.
All right, accept uncertainty because it's been proved psychologically that the best students are the one who can talk.
Well, we have actually a question in our comment section via Facebook Live. The question is, can you ask her, how can you capsulate the future of architecture in a short story in quantum perspective?
Capsulate the future of architecture using quantum
Mhm.
mechanics
Uh,
in a short
Yeah.
story?
Do you want me to read it again? I'm going to read it again.
Yes, please.
Can you capsulate the future of architecture in a short story in quantum perspective?
I thought I just did in a past hour.
um,
I'm sorry,
well,
what it
oh, it says here that in the perspective of quantum,
Mhm.
can you tell us like a short story on how can you capsulate the future of architecture?
Mm.
If one day we're gonna look back at it, oh, Architect Provide said this in quantum perspective. Mhm. Well, I get we were getting personal there, and then
That is a very okay. I feel like I guess it's okay. The main point is not to just look at it from the quantum perspective. It's more how to tie different scales. And I know architecture always talk about scale, but when we actually talk about scale in quantum mechanics, we are asking the most fundamental problem of the universe that all scientists are not able to explain. Like we understand certain rules at the quantum level, we understand certain rules at a biological level, we understand certain rules at a planetary level or interplanet level, but we're not able to understand the relationship. So for instance, how do we tie gravity force with quantum force? Because that's like a common mystery in the science field where we are hypothesizing there is a unified theory, but we're not able to unify it yet. So I guess the question is the same for architecture. within a building, it's a complex system. You have different components. When you're designing, for instance, a toilet, it's hard to imagine the whole building. When you're designing an urban system, it's hard to imagine the toilet itself. So I guess the problem is the same. Is how are you able to capture across scale, and especially with the computer systems that we have nowadays, are we able to have computational program where we enter parameters from different scale, we're able to output something? And if we're not, what ways can we sort of hypothesize and work based on this hypothesis? So I guess throughout the lecture, my point was that if we're able to have partial understanding or partial differential equation, we will be able to translate from natural language to mathematical language and be able to describe the system more comprehensively. And from that, we will be able to design. So I guess for architect, if we are learning from quantum mechanics, yes, it's very important to understand the science definition, but we do not forget that we're not scientists, we're actually designers. So what we can actually get out of is a way of thinking, is a way of reasoning, a way of understanding systems, and to be able to digest that and make it our own method of design. I don't think that's a story, but
But that answered a lot of questions. So I thank you so much for that. And as of the moment, there's this question that we have on the comment section that as an architect for focusing on preemptive design, what is the challenge in our environment nowadays that you see as a threat or very harmful to human?
do I know you? It seems like it's a no. I mean the guy who asked the question. I think he sounds like a friend. Not okay. He could be a real friend or a disciplinary friend. Either way. A threat. There are so many threats. Where do we even begin? I guess the most threat is dichotomy. I think that is embodied in our political system, in our market a lot, that you either have centralized, decentralized, left or right. And we don't forget that if we do not accept the difference, then we will not be able to preempt, no matter it is. For instance, if we take it down to a very practical level, Adobe is incompatible with AutoCAD, right? And we're not able to directly recycle, reuse, and translate all the information that we have generated from one to another. And that's the same. If the left and the right are always, it's good to oppose each other, but if we're not able to be compatible in terms of information, in terms of thinking of a way of information transfer, then we will not be able to preempt, because it means that every data that we've collected from one perspective is only operable in that perspective. And we cannot formulate, let's say, don't talk about planetary scale system. Let's just say a country scale system. We wouldn't be able to do that. So I guess one of the threats is that we do not have an alternative monetary system or funding model that allows us to be compatible. Like, would Adobe or AutoCAD be able to make everything for free at the same time generate, economic profit? Because that's the challenge. And I think with technologies like blockchain and stuff like that, we are seeing some opportunities. But I guess it's very important for a designer to actually understand what technologies are available, because people who design technology, they maybe don't understand the industrial need in social science a lot, and people who design for social science, they don't understand technology a lot. So I guess the largest threat is really this gap that we are not seeing. We don't even know where this gap is. And it's a threat where we have to work towards filling this gap.
Well, we have another question here that with biodesign, since it's the relation between individual and and the environment, what would be the effective ways?
Wait,
Effective
wait.
ways to safeguard the people, especially when our environment is already degrading.
With biodesign, what are effective ways to safeguard people, especially with our environment degrading?
Mm-hmm.
Well, I guess there are mainly two large approaches. One is to reduce on consumption. The second is to have circular economy, where everything that you created, it can be plugged back into the system from cradle to cradle, right? But so I guess when we're designing, we cannot just think about the individual design. For instance, a lot of bio-design are focused on material. So they focus on biodegradable material. If we look at plastics, it's not biodegradable, right? So, but we already are producing a lot right now. And the production of plastic, it's in a very complex economic chain that we cannot just say, okay, tomorrow we're not going to use it. But in what ways can we, transit from plastic to biodegradable? So one of the ways, for instance, we can look at Japan. What they do is that instead of having 12 different types of plastic, where it costs a lot to divide them, like you have to hire a lot of people to manually look at the bottom of your cup and then see, oh, it's type 1, and I put it in the type 1 bin. So that's why a lot of people, a lot of industrial operators are not willing to do that. But for instance, Japan, they just say, okay, you can only use type 1. And that already solved a lot of problem because you're minimizing the operational cost. So I guess for designers, it's important to stay in the shoes of people you don't agree with. So for instance, you would be like, why is the operator so evil? Why wouldn't he defy our plastic? But if you understand what are the difficulties, then you can design for him. So instead of just saying there's one building design and then I have to work on this one material, it's more like, how do I map different users who are going to be in contact with this material, and I design for him.
Thank you so much. And we have actually one last question, just one last question that I am also curious about. Can you share to us your skincare routine? Your skincare routine. Everyone is curious on the comment section. Everyone is asking about your skincare routine.
Really? My skincare routine.
That was just to break the series now.
Oh, okay.
But if you're willing to answer, we're gonna listen.
Yeah, I actually use this baby wipes. They use that to wipe baby bumps. So then I use that to wipe my face. I guess that helps.
That's really cute.
Yeah, if the producer is willing to harm babies, then I have nothing to say. But I guess baby products are safe, right? Anyway.
Well, thank you so much. Thank you so much. That was actually just to break the serious note, and thank you so much for laughing with me.
Thank you for the question.
Now we will be
Hi, Mariana.
awarding a certificate.
Hello.
Hi there, Mariana. Okay, so as for our certificate of appreciation, it's proudly presented to Architect Provides, and in grateful acknowledgement as one of our honorable guest speakers during the 11th Area D Assembly forthcoming What Lies Ahead, held on the 24th day of January in the year of our Lord 2021. Thank you so much, Architect Provides, and for laughing with us
That was
today.
fun. Thank you.
Thank you so much. We will be proceeding to our next speaker. As for our second speaker, she is an architect and urban designer from Portugal, recently working with Zaha Hadid Architects, teaching at the Architectural Association in London, and doing live workshop and webinars with students